All right. Well, welcome back, folks. I apologize about this weekend. I don't know what happened to the videos. They when I tried to upload them, they were not uploading. I don't know what quite happened. Maybe the file got corrupted somehow, maybe on my computer. Like I said, I don't know. So they weren't able to upload. So what I'll do is I'll post a second video this afternoon. I won't make any, I won't require that you turn it in, but that it'll be more of an informative video to get us caught up. I'll go ahead and do that this afternoon to make up for this weekend. Also, if you look on Classroom, I've already posted for us the next topic we'll talk about, which is Beer's Law, and then we'll finish up. And Beer's Law will go fairly quickly. I've posted there for you a FitLab also to help you with Beer's Law. And I'll talk about Beer's Law hopefully on Wednesday and or hopefully on tomorrow or Wednesday. And then what we'll do is we'll wrap things up with a quick discussion, an overview review of the material in chapter 10, which basically deals with the interactions between molecules and particles. And then we'll be ready for the exam next week. Okay, so please make sure you go online, go to the College Board website, check to make sure that you are there. As of today, they have the material needed and I think a practice for you possibly. And so go ahead and check there. Go today. There's an I think they've updated the material that you'll need to take the exam next week. Make sure you're all ready to go for next week, folks. We don't want to have to deal with any of the technical issues that may occur if we're taking an exam online. Okay, so please make sure you do so. I encourage you to make sure that you have everything ready to go. If you have any questions, email me or come on by at 1:30 today. I apologize for Friday. I had a meeting that was late, and I wasn't able to make the office hours. So if anyone tried to come by on Friday, I apologize for that. I'll come by today after school, and then I'll make it up for you. Okay, I'll make it up to you. All right. So hopefully that clears a few things up for you. But like I said, if there's any other questions, email me or stop on by after school today, and then we'll go ahead and talk about whatever you have concerns you may have or questions you may have. Okay. All right. So on Friday we left off with this problem here. What we were doing here, essentially, folks, and though it looks like there's these two diagrams, the diagram looks a bit confusing. Just make sure you understand that what we're doing is we are trying to find the electron configuration. We're trying to determine the electron configuration for molecules, and specifically we're trying to find the electron configuration for simple molecules. We're simply going to find them the electron configurations for diatomic molecules, and that in which the atoms are the same. But essentially, if you want to think about it, the bonding that occurs between atoms, even if we are looking at more complex molecules such as methane here, as opposed to nitrogen, okay, we typically only look at the bonding that occurs between two atoms at a time. We don't look at the bonding that occurs, the interactions that occur throughout the molecule. Okay, so with that said, when we talk about the molecular orbital theory, okay, we're assuming then, the assumption then is that the electrons are flowing throughout the molecule, okay? But what we do is we are analyzing one interaction at a time between two atoms, one interaction at a time, and the localized electron model proposes a very simple way that we can do that, okay, by looking at the bond here, and they refer to the bond as single bond, double bond, triple bond, okay? And so we can take a look at that as well. And but even with when we talk about the molecular orbital theory, the reason why this is useful for us in analysis of a simple diatomic molecule is because in essence here we're basically doing the same thing. We're looking at two atoms at a time, even though those two atoms are part of a larger molecule. We can look at those interactions, which accounts for the interaction of the whole molecule. Okay? When we do this, it is informative. Okay, and so when we try to write out the electron configuration for a simple molecule such as dinitrogen, okay, what we're trying to do then is we're trying to find then the location of the electrons that occur that holds those two atoms together. So the electrons and how they're being shared. Okay, so again, how these electrons are being shared between two atoms. Okay, between two atoms. And so finding electron configuration for this just allows us to place these electrons in terms of their energy. Okay, so remember what we're doing here is we're measuring the energy of the electrons. We're locating them very much like the same way that we located the electrons when we were writing out the electron configuration for atoms. Okay? So unlike with the electron configurations for the atoms and how we tried to locate it, we only had one diagram. Here we had two diagrams based simply on how these orbitals here and these orbitals here arrange themselves for a particular molecule. Okay? For certain molecules, then the sigma orbital formed from the atomic p orbitals here, they fall lower than the pi orbitals. And remember, these are the molecular orbitals here. On the sides here, these would be then the atomic orbitals, meaning then that this represents the 2s orbital, okay, here, or it could be the 3s orbital, and we'll see one of those in a moment. But we have to have then a situation where the atom has electrons in both the s and the p orbitals. Okay? And so you have here the 2s orbital and the 2p orbitals, and these are the atomic orbitals that we talked about. Okay? And so what we want to do then is we want to locate the electrons first, or each atom, locate the electrons first for each atom in the atomic orbitals here, and then we start filling in the molecular orbitals here. So if these represent on the side here, these are the atomic orbitals on the sides. These are the atomic orbitals. Okay. Remember, they come together to form the molecular orbitals here. Okay. And so these are the molecular orbitals for the molecules. Okay. So make sure you keep in mind atomic orbitals, molecular orbitals. Okay. These are the orbitals when the atoms are all by themselves. These are the orbitals that form when they get together to form this molecule. And so with that said, then we have two different configurations. We have two different ways that the molecular orbitals can configure themselves energetically. The only, for both of these here, the only real difference is how the sigma 2p and the pi 2p orbitals situate themselves. Okay, with one molecule, with one of the diagrams, with the sigma 2p orbitals lower in energy than the pi 2p, and the other one we have it flipped around. Okay? And we have experimental data to support one of these two diagrams here. And the data that we use then is going to be the data that comes from the magnetic properties of these molecules. Let me go ahead and erase this really quickly. The magnetic properties of these molecules, and also photoelectron spectroscopy, which I would like to start with hopefully towards the end of the period today. Okay. All right. So with that said, then that's what we have here. We want to locate this because we want to use those properties to help us. And so with that said, then I gave you yesterday on Friday, then I said then that with dinitrogen here, the properties of dinitrogen then is that it is diamagnetic, and that we know then for from so diamagnetic, meaning then that it has all paired, okay, which all electrons are paired. That means then it will not, it will be repelled from a magnetic field rather than pulled into the magnetic field. And so however we choose to do it, we have to make sure then that all the electrons, once we have it in here, they are paired. Okay? And then secondly, then we said then with the photoelectron spectroscopy, we see then that there are two electrons. There are a pair of electrons that are highest in energy, okay, that represent the highest in energy, and they have a different peak that is shifted higher in energy than all of the other ones. Okay. All right. So with that said, let's go ahead and write out the electron configuration. So with the electron configuration, we need to determine then the electron configuration for the atom. So a single nitrogen atom is 1s2, 2s2, 2p3. Okay, so we only focus in on these 5 electrons here. So we have 5 valence electrons coming from one nitrogen. We'll call this nitrogen 1. And then nitrogen 2, obviously, will also have the same exact electron configuration, 2s2, 2p3. Okay. Okay. So each nitrogen has 5 electrons that that will contribute to this here. So therefore, dinitrogen, then we have to account for 10 total electrons that dinitrogen coming from dinitrogen. Okay. All right. So let's go ahead and let's place these electrons here, these atomic level electrons on each side. So this side here will represent nitrogen 1. And this side here will represent nitrogen 2. And we'll do the same thing here, nitrogen 1. Nitrogen 2. Let's go ahead and place them in. So in the 2s orbital, we have 2 electrons. Remember with the arrows, each arrow here represents an electron. Electron spins have to flip. Okay, if they're going to share space, you have to flip. Okay, and with the 2p orbitals here, the electrons all spread out according to Hund's rule. Remember, when we fill the molecular orbitals, we will follow the same. We will use the same set of rules. Okay. All right, so and then with the off balance, so let's go ahead and start filling in the molecular orbital here. Okay, so make sure you do this, and make sure you have this chart in front of you. I did ask you to have print out this copy of this and fill it in. Later, then you should be able to do this without using this table here. Very much like with the when we did the electron configurations for the atom, we were able to kind of figure out through memorization by doing it enough that you can determine the electron configuration without the table, okay, without this diagram, without the chart. Same thing with these orbitals, with these molecules here. At some point, hopefully with tonight's homework, you practice it, you'll be able to write out these electron configurations without use of this diagram here, because there's no guarantees, and I doubt if they will give you this table here on the AP exam. Okay. All right, so the order of filling then is always going to be lowest energy level first, lowest orbital first, which is this pi, and this is the pi, the sigma 2s orbital. Okay, so 2 electrons will fill in here. Remember, lowest energy orbital fills in first according to the Aufbau principle. And the lowest, and in each spacing, you can only fit a maximum of 2 electrons according to the Pauli exclusion principle. So there it is. The sigma 2s orbital now is filled. Okay. Then the next orbital up is going to be the sigma antibonding, sigma 2s antibonding orbital. And remember, these can be occupied if we get stability elsewhere. Okay. Okay. So 2 electrons fill in there. There are the 4 electrons from either side here. So we have accounted for 4 of the 10 so far. We have 6 left to fill in. So these are the 6 we have to fill in here. Starting with the lowest energy orbital here, which would be the sigma 2p orbital. Okay. That will get filled with 2 electrons. Okay. 4 left over. Okay. So we'll fill in the pi 2p here. Okay. First, Hund's rule tells us then if we only have 2 electrons, they will spread out, but that's only 4 of the 6. So we have 2 more to fill in. And according to the Aufbau principle, they will fill in, and the Pauli exclusion principle, they will fill in lowest energy levels first, flip their spins in order to accommodate each other. And so there it is. That is the electron configuration for dinitrogen. So this is the first option here. So let's go ahead and write out the electron configuration for this one. Okay. This one then is going to be sigma 2s, and this is a general chart that I use here, so I don't write in the 2 here because we can use this for period 3 elements as well. Okay, so then if that's the case, then this would be a sigma 3s, and we'll see an example of that in just a moment. And this will be sigma 3s, and all these would be 3s. So each one of these here would be molecular orbitals coming from the second energy level, so we will call this sigma 2s. So we have then 2 electrons there. And then we have sigma 2s antibonding, and we have 2 electrons there. We have then sigma 2p bonding with 2 electrons here. And I'm sorry, this should be 2. That looks like 4. Okay, that should be 2. Okay, and then we have pi, okay, 2p, and we have 4 electrons there. So according to this energy diagram, okay, this is the electron configuration. Now, what we have to do is we have to support this proposal here. If this is the correct electron configuration, we have to measure it up against the magnetic properties of the atom, of the molecule itself, and the photoelectron spectroscopy for this molecule. And we'll get to that in just a moment. And so we'll compare it. Okay? So with that said, then before we do, let's go ahead and find the alternative. So this is option number 1. This is option number 1 for the molecular for the electron configuration for dinitrogen. Let's take a look at the second possibility. Okay. So we have, let's go ahead and fill in our atomic orbitals again. Okay, we have 1, 2, 3, 1, 2, and 3. Okay, let's go ahead and fill it in. Lowest energy level first. So we have then 2 electrons in the sigma 2s, 2 electrons in the sigma 2s bonding, 4 electrons here. Remember, they're going to spread out. Okay, 1, 2, 3, and 4, and then 2 electrons here. Okay, so writing out the electron configuration for dinitrogen according to this energy diagram here, then it would be sigma down here, 2s. We have 2 electrons. Sigma 2s antibonding with its 2 electrons. Pi 2p with its 4 electrons, and sigma 2p it's 2 electrons. So that is option number 2 for dinitrogen. So this is number 1. This is electron configuration number 2, right? So let's go ahead and write down what you were told. Okay, you were told then that first of all, that dinitrogen is diamagnetic. Okay, so diamagnetic meaning then that all electrons are paired. Okay, so if you take a look at this, then both options give us that. So option number 1 and option number 2 have all of their electrons paired. There are no unpaired electrons. And again, don't look at the sides here, folks. Okay, those are atomic orbitals. We're looking at these electrons here in the molecular orbitals, and every electron is paired in this model, in this this model here, in this option here, and all electrons are paired in this option here. So both models seem to confirm that the support then the fact that the molecule is diamagnetic. Okay. All right. The second piece of evidence we have then is the photoelectron spectroscopy evidence, and this one told us then that we have a situation with 2 electrons that are our highest in energy. This represents the electrons that are highest in energy. So therefore, we only have 2 electrons that are higher in energy than everything else. And if we consider, so remember, energy increases. So these electrons down here then would be the lowest in energy. These electrons here would be the highest in energy. So we're going to be looking at these here. In this particular model here, we are seeing then that we have 4 electrons that are higher in energy than everything else, which does not seem to confirm what we have here. It does not seem to confirm what we have here. Whereas if we take a look at this model here, we have 2 electrons that are highest in energy. Okay, they are highest in energy, and so therefore, based on the 2 pieces of evidence here, this proposal here, this model, this electron configuration then represents the electron configuration that is correct for dinitrogen because it corresponds to the experimental data that we collect. Okay? And so this one would be the incorrect model for dinitrogen. And so this, folks, is how we go about determining then electron configurations for diatomic molecules. Okay. All right. Very good. Let's go ahead then. Let me ask you to do one more really quickly. Okay. Let's do one more, and let's. Okay. So let's do it for oxygen now. Okay. Let's do electron configuration for oxygen. Let me go ahead and give you the information for oxygen really quickly that you'll need to support your answers. Okay. So with oxygen, then we are told that oxygen is paramagnetic. So, number 1, the evidence then is oxygen is paramagnetic. Okay. Okay. Also, oxygen then has 4 equivalent electrons that are highest in energy. Okay. So we have 4 electrons highest. I'm sorry. This is photoelectron spectroscopy. That's spectroscopy. Okay. So from photoelectron spectroscopy PES data, okay, we have then 4 electrons. I'm sorry, 2 electrons that are highest in energy. Okay, that represent the highest energy. Okay, so we have 2 electrons highest in energy. What I'd like you to do then is go ahead real quick to take about 3 or 4 minutes to fill in this table here using this data here, using this data that you have. Okay, and then work it out, and then let's see what you have. So we have the oxygen, again, is paramagnetic. The evidence shows us that oxygen is paramagnetic, and that there are, from photoelectron spectroscopy, there are 2 electrons that are higher in energy than every other electron. Okay, so using this data here to help you determine then what is the correct electron configuration for oxygen. Okay, so go ahead and try that really quickly, and then when you get back, we'll go. Okay, so if you want to, make sure then that you print out a copy of this table here again, and then go ahead and get that, and then write out your electron configuration. Okay, all right, go ahead and try that, folks, and then we'll get started with it. Okay, let's go ahead and let's take a look at what we have here. Okay, so let me go ahead and clear this up. Okay, so there's the data. Make sure you've written that down. Okay, let's go ahead then and let's write down first and foremost so this is option number 1. Let's go ahead and do that. This is option number 1. This is going to be option number 2. Okay, And so let's go ahead and write out the electron configuration for each option. We'll call this option 1. That's going to be 1s2, 2s2, 2p4. Okay. 4, 5, 6, 7, 8. Make sure that I got that right. So with that said, let me. Okay. All right. So with that said, then 4, 5, 6, good. And then option number 2 here will be also 1s2, 2s2, 2p4. Okay. And for what we're going to do then with since we're looking at dioxygen here, which is the molecule, the diatomic molecule we're looking at, we're only going to examine then the valence electrons here. Okay, so we have then 6 here total, so for each side, so we will be having to account for 12 total electrons, for dioxygen. Okay, so let's go ahead and fill in the table now. These are 2s orbitals here. Okay, these will be your 2p orbitals here. Okay, let's fill in the atomic orbitals first. So you have 2 electrons in the 2s orbitals, and then 4 electrons, okay, in the 2p. So there are the 4 here. Okay, same thing for oxygen number 2 here. So this will be for oxygen 1. This is for oxygen 2. Okay, so let's go ahead and fill that in. 2 electrons here. 1, 2, 3, 4. Okay, so so those are the atomic electron configurations, okay, for the valence electrons for oxygen. All right, let's start filling in then our molecular orbital diagram here. Okay, so 2 electrons here, so sigma 2s. Okay, there will be 2 electrons here. Okay, and then we have then 1, 2, 3, 4. So remember, we have to account for 1, 2, 3, 4, 8 electrons. So it's 2, 4, 6, 8, and then this is Hund's rule tells us that these will spread out there. Okay. All right, so let's check to make sure that we've accounted for all 12. We have 2, 4, 6, 8, 10, 12. So there it is. So this is the electron configuration. Let's go ahead and write this out, what we have here then. This is going to be sigma 2s, 2, sigma 2s star, 2, sigma 2p, 2, pi 2p4, okay, and then antibonding pi 2p antibonding 2. So this will be option number 1 for electron configuration for oxygen. Okay, so let's go ahead. That's option number 1. Let's go ahead then and do the second one. Okay, so we have then oxygen 1, oxygen 2. Okay, we have 2 electrons on either side. 1, 2, 3, 4. 1, 2, 3, 4. Let's go ahead and start filling it in. We have then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right. So with that said, then let's go ahead and let's write out the electron configuration for this one. This is going to be sigma 2, 2s, 2, sigma 2s star, 2, okay. Pi 2p 4, okay. Sigma 2p 2, and pi a pi 2p antibonding 2. So we got 2, 4, 6, 8, 10, 11, 12. Okay, so we have 2, 4, 6, 8, 10, 11, 12. Okay, so this is the second option for electron configuration for dioxygen. Okay. All right, so let's go ahead then. Let's compare then the data here. So first of all, we said then that this molecule is paramagnetic, which means then the molecule has unpaired electrons. Here we see then that in this particular model here, that has 2 unpaired, and this one has 2 unpaired as well. So both models seems to suggest then that both of them give us then the unpaired electrons. So both of those right now fit the paramagnetic data, okay? The data for the magnetism. All right, let's take a look at photoelectron spectroscopy data, okay? And let's go ahead and take a look at that one really quickly. Okay, so What I gave you then with the PES data is that I said then that there are 2 electrons that are highest in energy. Highest in energy are 2 electrons, highest energy. Okay. If we take a look at this here, we seem to see then that both this one, you have 2 electrons highest in energy here, and then 2 electrons that are also highest in energy here. So if that was the only piece of data, those are the only 2 pieces of data that we have, both of these electron configurations seem to confirm then, seem to are supported by the data here. So PES data, and we're going to continue this, it gives us the energy for all of the electrons, gives us the energy for all the electrons. So this will represent, and you'll see this in, this afternoon, okay? You'll see then that this will represent one peak shifted furthest down on the energy diagram, okay, for the PES spectrum, okay? But there are other peaks. And so what you want to do with the photoelectron spectroscopy data is look at all the peaks that are given to you. And so with that said, then if this is highest energy, you shift down, and then you realize, and then you'll see then that there are the next peak that represents 4 electrons that are next highest in energy, okay, next highest. Okay, and so if you take a look at this one here, you're going to see then that there are your 4 electrons. You have 4 electrons, so you have 2 electrons highest in energy, okay? And then the next one then is you're gonna have 4 electrons, okay? Here, you only see 2 electrons highest in energy. And so therefore, the correct electron configuration for dioxin will be this one, okay? Where you have 4 electrons next highest energy, not just 2. So this is why photoelectron spectroscopy is going to be absolutely important for us in determining electron configurations, not only for molecules, but we can also use photoelectron spectroscopy to locate atomic electrons at the atomic level as well. Okay, so this is one way that we can confirm that we have the correct electron configuration when quantum mechanics tells us that we don't know the exact location and position of the and speed, the momentum of an electron, but we can place it energetically. Okay? All right, so with that said then, let me just go ahead and summarize this up for you folks. Okay? And so if we take a look at this table here, okay, if we take a look at this table here, it kind of gives us then the electron configurations for all of the nonmetals in period 2, okay, all the nonmetals in period 2, and that's what we're concerned with. Now, with what we did when I introduced molecular orbitals to you, we looked at the electron configurations for metals. We saw dilithium, we saw diberyllium, but really, when we consider the molecular orbitals, we're going to apply it to non-metal atoms, because it's non-metal atoms that covalently bind together and share their electrons for the most part to form these molecules. Okay? And so here are the remaining, we did diboron, we did dicarbon, we did dinitrogen here in this table, and then I give you here the difluorine as well. Okay? And so with that said then, these are for the period 2. These are the period, so this is period 2 elements, period 2 nonmetals. Okay, and so this table here summarizes the period 2 nonmetals. It gives us the electron configurations here. Okay, so hopefully from this you should be gives us the table here, the diagram for each one of these. And if you notice here, this represents one possible diagram for the molecular orbitals, and this represents another one. If you take a look at this, then the pi 2p here is shifted, and the pi 2 shifted here and there. Okay. And so with that said, then you see then the diboron, dicarbon, dinitrogen, when we write them out, they will use the first model here, okay, to fill in their electrons, and with oxygen and fluorine, okay, they will use the second energy diagram to fill in the electrons. And these electron configurations are supported by the properties here of the molecules listed here for you. What I have not listed for you here is the photoelectron spectroscopy. This table doesn't list that for you, but it does list the magnetic nature of these molecules. And then they give us the bond order. A couple other things that we can use a couple other pieces of evidence that we can use to support our data here. The bond energy, which we can measure, and the bond length too, that can be calculated. Okay, so we use that to other pieces of evidence to support the electron configurations that we have here. So what I would suggest you do then is We've written out the electron configuration for dicarbon, for dinitrogen, and dioxygen. Okay, right out the and we did it for diboron. Write out the electron configuration for difluorine. Okay, so what I would like you to do then is to finish up on your paper. What is the electron configuration? So right now that you have it here, electron configuration for difluorine. Okay, so write that out. Okay, so write out the electron configuration for difluorine on your paper and turn that in with the rest of the work that you did. Okay. And then what we'll do is this afternoon, we'll continue on with the discussion of these diatomic molecules. And then I would like to get started with the discussion of photoelectron. I'm sorry, we'll talk about these are homonuclear diatomic molecules. I'll just quickly mention heteronuclear diatomic molecules, what they are. We won't go into those too much because I would like to start in with photoelectron spectroscopy this afternoon. Okay. All right, very good, folks. Have a good rest of your morning, and I will see you this afternoon.